Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at the production of one of the group 3 elements, and this is going to be the production of aluminium. Before we proceed, I kindly like to appreciate our incoming members and also request them to be engaging us in the comment section, subscribe, and also be checking our description boxes of various uploads. Now they're going to contain links of other videos which of course are going to be concerning the similar topic under discussion. In this specific case, we have decided that we're going to look at a range of elements across the periods and of course down the groups. And in the group 3 elements, we're going to see that aluminium as one of the elements of this specific group, apart from boron, gallium, indium, thallium, is going to display some of the properties which we are going to see. And of course, they are going to be unique in a way that it's going to be contrasted from other members of this specific group. Now, concerning the production of aluminium, of course, this is going to be also relying on its physical and chemical characteristics. But of course, we're going to see that at some point in along the specific timeline in history, there was a difficulty in extracting it from its ore. And of course, we had said that this specific element is going to be found from the chief ore, which we had said was bauxite. And of course, this was a hydrated form of aluminium, which we are going to see later in our discussion, being given as this specific, of course, hydrated salt. Now, in this specific hydrated oxide, now in this specific case, there's going to be some methods which are going to be used in attaining aluminium from this specific ore. But it's good for us to appreciate this specific development which are mentioned along the historical timeline, which we have said that around this specific period of the 1886, the period preceded this specific period created a lot of difficulty in trying to obtain aluminium from its also due to, of course, the limitation of some of the methods that were available. But of course, this specific point, there was some means which were devised in trying to obtain aluminium from its ore. Now, the first, of course, this specific element was first isolated from, of course, or was first isolated by a Danish chemist by the name State. I hope my pronunciation is going to be correct. Now, this is important for us to mention since we have said that some of the elements in the periodic table are going to be named after the names of individuals, or perhaps in some of the activities like the radioactive elements which are going to be associated with some kind of activity. Of course, measurements which we are going to come across are going to be named in one of some of the scientists. So in mentioning this one, of course, we are going to appreciate in case we come across it in some of our discussion. Now, concerning this specific distribution, the element or the oxide of aluminium, which we have mentioned, is widely distributed in some of the geographical regions which we are going to see. And of course, to mention a few, we're going to see that in the continental United States or America, especially the US, it's going to be found in this specific place. And of course, in Guyana, and then we are going to see that this also is going to be distributed widely in some of the areas in the continental Europe, given as such. Now, of course, there were some methods which were advised, which are aside, of course, in trying to, of course, obtain this specific element from its ore, and they were advised in this specific period which I've mentioned. Of essence for us to look at was the works of Martin Hall, who of course was an American chemist who came up with a method of extracting this specific aluminium through the process of electrolysis. And him together with, of course, Harold, we're going to see that they are going to come up with a specific method of trying to find an efficient way of separating this specific ore from or element from its specific ore. One of the characteristics that we're going to witness that perhaps created some of the difficulties in trying to obtain the element from the ore was its melting point, which basically is around 2020 degrees Celsius given as such. Now, Hall and Herold came up with a method of using cryolite, and we're going to see that this basically is a compound of sodium, which is going to be, perhaps I can give this one in terms of ways so that we can be able to follow. So we're going to see that the two individuals came up with a method of course, separating aluminium from its ore using electrolysis. And we're going to see that they introduced this specific compound, which we refer to as cryolite, of course, which is a compound of sodium, which we're going to give as sodium, the aluminium, and fluorine. So this specific compound is going to lower this melting point of, melting point of the aluminium oxide, and we're going to obtain an efficient way of trying to, of course, apply this specific process of electrolysis in trying to obtain the element of aluminium from its specific ore. Now, in this case, we're going to look at a summary of this specific process in terms of perhaps equations, and of course, we shall look at perhaps a small scheme of this whole process so that we are able to appreciate the historical development and some of the inputs which were put or which were given in order to come up with the element of aluminium. Now, in this particular case, I've mentioned that the chief ore for obtaining aluminium is bauxite, and therefore we are going to look at some of the properties of this specific oxide, which is going to assist us obtain our final element of aluminium. Now, bauxite contains an impurity of iron, of course, 2 or iron 3 oxide given as such, and this impurity is going to be removed during its specific process of course, processing. And of course, there is a principle that is going to be used in trying to separate aluminium from its oxide, particularly in the small scale, and then we are going to look at the commercial separation that is going to entail the Hall and Herold process, which of course I've mentioned in my previous statement. Now, in this case, one of the characteristics of the oxide which we're going to see is that it can be it can react with the base. Now, in our last discussion, we had mentioned that basically one of the applications of aluminium is it's used to protect the aluminium oxide. It's used to protect metal surfaces from rust, since it's going to be water resistant in this specific form. But we have said that this specific oxide is susceptible to reaction by acids and strong bases, and therefore we're going to see that this characteristic is going to assist us in trying to obtain various other compounds from aluminium oxide, which are going to be assisting us in trying to understand the concept of the whole process. Now, in this particular case, therefore, we're going to look at the reaction that is going to involve the reaction between aluminium oxide and a base, and of course this is going to be given in this specific equation. So we shall have this one. So we have given this version of the equation in our previous discussion, and therefore this is going to be 3 molecules of water, and we shall have a formation of this complex oxide, hydroxide given as such. So we shall have this one. So these are 4 hydroxide ions given as such, and this is going to lead to the formation of an aqueous complex ion given as such, and therefore that's going to give us one of the characteristics of aluminium oxide, which is going to be reacting with the bases. Now, in this specific stage, then therefore we are going to see that this particular compound, whenever it's going to be solidifies, it's going to slightly precipitate and give aluminium hydroxide. And of course, this is going to be one of the ways in which we can obtain aluminium from these specific hydroxides. Now, I've mentioned that this specific, of course, complex ion can be solidified, and then it's going to slightly precipitate, and of course it's going to be slightly precipitating this specific, of course, hydroxide that's going to be aluminium hydroxide given as such. Now, heating this specific, of course, precipitate is going to result in the formation of aluminium oxide and of course given as such. So we're going to have aluminium oxide given as such, and then we shall have the formation of water. So I've just written this one in terms of a schematic so that we can be able to follow, but we need to write this equation from this one, of course, and forming these specific products given as such. So in this particular case, we're going to see that the aluminium oxide can react with the base to form a complex ion, which upon solidification is going to form a precipitate of aluminium hydroxide. Upon heating this one, this is going to lead to the formation of aluminium oxide, which of course we have seen is going to be that specific, of course, all parts which is going to be losing this water, of course, which we have given as such. So it's going to be not an hydrated salt, which is going to be obtained at this specific point. But one of the challenges of obtaining aluminium from this specific point, they mentioned that this is going to have a melting point of 2020 degrees Celsius. And therefore, Hall and Herold came up with a procedure for trying to obtain this specific product of aluminium from this oxide by introducing cryolite, which of course, I said, is a compound of sodium, aluminium, and fluorine given as such. So we're going to see how this one is going to be taking place in the reaction in order to lead to the formation of aluminium. And this specific process that was introduced by Hall and Herold, of course, was found, the two found independently that aluminium oxide by mass can be dissolved in cryolite, and of course, this is in the quantity of around 15%. And of course, this specific solution which is going to be obtained can be electrolyzed, of course, to achieve this particular product of aluminium as said. So this is going to occur in molten cryolite and a particular temperature. Now, one of the advantages of this specific introduction of cryolite is that this is going to decrease the melting point from 2020 to around 800 to 1000. And of course, now that's going to be assisting us in trying to obtain the final product. Now, perhaps if I may write it in terms of a scheme, so we have said that we are going to have this specific aluminium oxide being obtained, of course, from this specific process. And of course, we had said that this aluminium oxide is going to be introduced in cryolite. And of course, this is going to be molten cryolite at a temperature of around 800. So we're going to have in some text this given as 1000 degrees, at around 1000 degrees centigrade. And of course, this is going to be appearing in terms of molten aluminium. So this is going to be a solid, but this is going to be molten aluminium in cryolite. And then therefore, this is going to be electrolyzed in order to obtain the final product. Now I'm going to give you a unique equation of this specific process, which is going to result in the formation of a final product, and they're going to assist us in understanding better the formation or the summary of this specific process. Now we are going to have of course the furnace in which this specific reaction is going to be taking place is going to be lined with the carbon. Now we're going to see that the carbon also is going to be taking a part in this specific reaction, in a sense that, as we had said, from the process of electrolysis, there are some preference for particular ions which are going to be released at the anode and the cathode. And of course, we're going to see that carbon is going to be one of the, of course, products which are going to be involved in this specific whole process of obtaining of aluminium. So we're going to have this summary of the reactions, whereby we're going to have carbon reacting with this specific, of course, we're going to give these specific negative ions of oxygen, and I'm going to explain where they are going to be derived from. So this is going to be reacting with this one, leading to the formation of carbon 4 oxide. Now, in some cases, we're going to see that depending on the volume, they're going to form carbon 2 oxide. And of course, these are going to be in 3 units, as I've said, using this specific illustration. So therefore, I'm just going to go with this. So this will be erosion of the electrodes which are going to be used in this particular process. Now I've mentioned that this furnace is lined with, of course, it's a rectangular steel container that is lined with the carbon, and these are going, the carbon are going to form what we refer to as the cathode. Now inside this container there is going to be, of course, a suspension of the carbon rod steel which are going to be used. So I've said that this is going to be a steel container, but it's going to be lined using carbon given as such, and there are going to be electrodes which are going to be used in this specific molten graphite, of course, and aluminium, or which are going still to be carbon in that specific case. So this is going to be the overall reaction which is going to be taking place on those specific carbon. Now the charge which is going to consist of this graphite is going to melt and an electric current, and of course that's going to also act as this specific, it's going to act as a flux and a solvent at the same time. Now aluminum is going to be, of course, obtained from this specific bauxite through this general reaction, whereby we're going to see that the oxide of aluminium is going to be undergoing, of course, a reduction, and we're going to have the production of oxygen and aluminium given as such. So at the anode, at the cathode, which is going to be attracting the positive ions, we're going to have the release of aluminium. So therefore we shall have just an ionic equation at the cathode, which is going to be 4 units of aluminium ions. They are going to undergo reduction, and this is going to form, of course, aluminium solid given as such. And of course these are going to be 4 units. So for essence, for us to understand, we're going to have this specific equation for carbon, and then we shall have an equation at the cathode which is going to be given as such. And lastly, we're going to have for the equation at the, particularly this is going to be the equation at the anode, and then we shall have the equation at the cathode given as the second one. Now the overall equation for this specific reaction is going to be, from the sides of the reactant, for this ionic equation, we're going to have, let me just give this one. So we're going to have 3 units of carbon, which I've given in this specific case for this particular processing. And then we shall have this specific ions of aluminium. So we're going to have plus 4. These are going to be ions of aluminium, which I've given in this specific equation. And then we shall have this specific 6 units of this specific ions of, so we shall have 6 units of O2 negative, and then we are going to have 4 units of this specific aluminium being produced as a solid, and then we shall have this specific units of oxygen which are going to be produced. So we shall have this one as given as such. So this is going to give us an overall equation for the production of this aluminium, and this is going to form a final bit of this specific production process. Of course, this has been compacted, but we're going to look at this whole process in our various discussion, perhaps in terms of a question set, and that's going to be more elaborate for us. So that is it for now, guys. Bye, God bless you. Catch us in our next video.